All right, welcome everyone. We're going to get started today. All right, so just a few reminders before we do get started. We have homework due tonight on Learning Outcome '05. So kind of using the first derivative test and the second derivative test to classify our critical points. And then on Thursday, we have homework for '06 due. So those are kind of our applied optimization problems where we have an objective function and a constraint function. And then for next week, Tuesday, we have homework for our integration due. So just a reminder about a couple of the homework assignments that are coming up. All right, so let's continue on. We're going to finish talking about indefinite integration today. And we're going to look at, just to quickly discuss here, the variables. So, you know, a lot of times we're going to be doing integrals involving other variables besides just the usual x and y. So, you know, but the integration process is really going to be the same, you know, just different variable. So you just want to be careful and consistently use whatever variable you start with. So in this little example here, you know, how would we go about doing the integral of x squared dx? Well, just basic power rule. So 1/3 x cubed plus c. And so if we were doing the integral of, say, t squared, the process is exactly the same. Same power rule, we're just using variable t instead. So this would be 1/3 t cubed plus c if we were doing the integral of t squared. Now, one thing to note here is that our integral notation does give us some indication of what our variable should be. So when we look at the differentials here, the dx and the dt, those differentials tell us what our variable is. And so our differential here at the end of our integration sign, this is something that we're going to pay attention to, and it's going to become pretty important for some of our later topics. So this differential, it tells us what variable we are integrating with respect to. So in that first integral, we were doing the integral of dx, or the differential was dx. The x there tells us our variable is x. In the second integral, it was dt. The t tells us our variable is t. So we want to be just aware of what that differential is telling us. And we'll definitely going to be paying attention to that in probably on Thursday and some of the topics we talk about on Thursday. So that differential becomes important. So you just want to be consistent. Whatever variable you're using, you just want to be consistent. So that's really the lesson here. So if you start with an x, make sure you finish with an x. If you start with a t, make sure you finish with a t. All right. So last time when we were talking about integration, we kind of looked at some of our indefinite integration rules. So sum, subtraction, constant multiples. We looked at power rule. So these are all of our basic integration rules. And we've been integrating kind of power functions so far. And we really want to kind of expand our horizons and consider other functions, maybe trig functions, inverse trig functions, log functions, exponential functions. So we want to be able to potentially integrate those types of functions as well. And we've seen how to do derivatives of those. So we had these derivative tables for all of our elementary forms. And we looked at this way back when we talked about derivatives. And the way we would use these tables is if there was a function that we wanted to differentiate, we would just come to the table and find the function in the one column and see what the derivative is in the second column. So for instance, if we wanted to figure out the derivative of, say, sine of x, we would find sine of x and then just read over and see what the derivative is. In this case, cosine x. So the way we would read these tables is, for instance, derivative of sine x is cosine x. So we would find our function and then look it up, and that would tell us what the derivative is. Now, the nice thing about these derivative tables is we can use them to help us with integration, because differentiation and integration are basically reverse processes of each other. So if we wanted to, say, figure out the integral of cosine x, well, we could just go in reverse. And that gives us the integral of cosine x. So if we were trying to figure out, say, the antiderivative of cosine x, well, using this table, we would see that that antiderivative, that integral, would be sine of x plus c. And so these derivative tables, we can really use those to help with our integration. So for instance, with this sine and cosine one, when we look at this, the cosine x term on the right, that's our derivative. And the sine x term inside the brackets here, that's our antiderivative. So when we have these derivative formulas, derivative of sine is equal to cosine, well, the term on the right there, that's our derivative, and then the term inside the brackets, that's our antiderivative. So we could write that instead as an integral formula and say the integral of cosine is equal to sine. Let's try another one of these. Let's look at natural log absolute value x. And we see that if we were interested in finding the derivative, what would be the derivative of natural log absolute value x? Well, based on our elementary form table here, the derivative would just be 1 over x. So the 1 over x, that's our derivative. But if we were interested instead of finding an antiderivative, that natural log x, absolute value x, would be our antiderivative. So another way to kind of write this, if we were more interested in integration, is to say the integral of 1 over x, or the antiderivative of 1 over x, is equal to natural log absolute value x plus c. So we can use these derivative tables and just kind of work backwards. So work backwards to figure out what the integral is, what the antiderivative would be. So we could, in essence, have a separate list table of elementary form integrals that we could memorize, but really it just comes back to our derivative tables. So these are going to be our elementary form indefinite integrals, but really they're coming from our derivative table as well. So we'll read through them and we'll mention a few things here, particularly about that 1 over x, because there's a little subtlety here that's worth mentioning. But first, let's just read through these. So the antiderivative of e to the x is just e to the x plus c. So that's a nice one. Is the integral of e to the x is its own function. The integral of 1 over x we just saw was natural log absolute value x. Then the integral of sine is equal to negative cosine. And the integral of cosine is equal to sine. The integral of secant squared is equal to tan. The integral of cosecant squared is equal to negative cotan. And we're putting plus c on the ends of all of these. Integral of secant times tan is secant. Integral of cosecant times cotangent is negative cosecant. And then the integral of 1 over 1 plus x squared is inverse tan, or arctan. And then the integral of 1 over square root 1 minus x squared is inverse sine, or arcsine. And I might have skipped over integral of secant squared is tan, and integral of cosecant squared is negative cotan. So, you know, these tables here, this table of elementary forms, if we just go back to our derivative table, it's really nothing new. So how did we get, say, the integral of secant squared? Well, we just went backwards. Integral of secant squared is tan x. And that's precisely what we're seeing on our table here. Integral of secant squared is just tan x. All right, so these are our elementary forms. Probably easier just to have these memorized, though. Now, there's a question about 1 over x and that natural log absolute value x. And I want to mention it here because this is, it's subtle, but it's important. So there's a few things. So the first thing is when we are figuring out our antiderivative, we want our antiderivative and our function, our original function, to have the same domain if possible. So we want our antiderivative capital F of x to have the same domain as the function we're trying to integrate, little f of x. So really this comes into play with that 1 over x function. What is the domain of 1 over x? Well, the domain of 1 over x, I'll write it over here, is everything except 0. So 1 over x is defined everywhere. The only time it's undefined is when we try to divide by 0. So we want our antiderivative to have that same domain. So we want the antiderivative, which is, what is the domain of our antiderivative if we have that absolute value x in there? Well, it's also everything except 0. So with that absolute value, normally with natural log we can't plug negatives in, but that absolute value helps us out. We can plug negatives into that absolute value, and the absolute value kills off the negative, and then, you know, it's defined. So the domain of 1 over x is everything except 0. The domain of natural log absolute value x is everything except 0. So that's an important little distinction there, is we want our antiderivative, if possible, we want it to have the same domain as our original function. And then one other technical point when it comes to this 1 over x, and in fact any of our undefined functions like 1 over x squared or 1 over x cubed, anytime we're dividing by 0, is when we say the antiderivative of 1 over x is equal to this natural log absolute value x plus c, the fact that 1 over x is undefined at 0, what we really mean by this is we mean the integral of 1 over x dx could behave a little bit differently on either side of 0. So we could think of this as a piecewise function where it's the natural log of absolute value x plus some constant c1 if x is greater than 0, and it's the natural log of absolute value x plus c2 if x is less than 0. So when we have this discontinuity, our original function here has a discontinuity at x equals 0, what could happen is on either side of that discontinuity, that plus c could be different. Our constant term could be different on either side. And so the same kind of idea applies for functions like 1 over x squared. Even though we'd use power rule for that, same idea. It's undefined at x equals 0, so you might have different constant terms on either side of that undefined x value, or that discontinuity. So just a few technical points there. We want our antiderivative to have the same domain as our original function if possible. And then if our function does have an undefined point or a discontinuity, then that plus c constant can be different on either side of that discontinuity. One other thing, if we're going back, kind of related to the question, if we're going back to our derivative tables, you might notice if we're working backwards, if we wanted to do the antiderivative of, say, 1 over square root 1 minus x squared, we kind of see that showing up two places here. So the general convention is, we say the antiderivative of 1 over square root 1 minus x squared is inverse sine, but we could also say that it's negative inverse cosine. But to make things easier for ourselves, we just kind of use the inverse sign so we don't have to worry about a negative. So just another little comment there. All right, so those are our elementary forms. Maybe one more here. If our function was not e to the x, but if it was b to the x, what is the antiderivative of that? Well, very similar. It'd be b to the x over natural log b. So maybe that's one more you kind of have tucked away in case we're not generally dealing with, say, a natural exponential function. We can do exponential functions with a different base as well. All right, so those are our elementary forms. How are we going to use them? Well, let's try a few examples. So let's look at the function 2 times sine x plus 3 times secant squared. And we want to find the antiderivative of this function. So we're going to use these elementary forms, and we're going to use our rules that we saw last time. So when we go about this, we look at our first term. So when I look at this, I see the first term, and then I see a second term. And they're separated by a plus or a minus. So the first term is 2 times sine x. And that 2 is just a constant multiple. So what we can really do is just focus in on the variable part, which is the sine x, and get the antiderivative of that. So the constant 2 is a constant multiple. It stays in front. And then we want to know what is the antiderivative of sine x. So we go to our table. We find sine x, and we just look it up, and it's negative cosine. And that's the antiderivative of the first term. Then we have a plus sign, so our antiderivative is going to have a plus sign. And then the 3 is a constant multiple, so it just stays in front. And then we really focus in on the variable part. Let's get the antiderivative of secant squared x. And so we go to our table, we find secant squared, there it is, and then we just look up the value. So it's tan. So the antiderivative of secant squared is tan. And then very last thing is we put the plus c at the very end. And we only do it for we do it for all of them. So just 1 plus some constant at the end there. And that's the way to go about it. So there's really not too much work to show for these. We don't generally show the constant multiple rule. We kind of just do it. Same thing with sum and differences. We just kind of apply the rule without really showing the work. And this is kind of how to think about it. You're just going term by term and doing term by term integration. Maybe the one thing you do after this is just to clean it up. I would bring that negative in front, so I'd write it as -2 cosine x plus 3 times tan x plus our constant c. Let's try another one. So see how the term by term integration works. And in this next one, we're going to do the integral of cosine theta over sine squared theta plus 5 over 1 plus theta squared. And we're integrating with respect to theta. So we're using a different variable here, but that's okay. Process is going to be the same. Now the difficulty here is that cosine theta over sine squared theta, if we go to our list of elementary forms, I don't see that exactly written on our list there. So we might have to try using some trig properties or just try rewriting that to get it in the format of one of our elementary forms. And that's what we're going to do. So before we even start trying to do the antiderivative, we're going to rewrite our function. And how we're going to do this is we're going to try to rewrite that expression involving cosine and sine squared. We're going to try and relate that to other trig functions. So maybe secant, or maybe cosecant, maybe tan, or maybe cotan, and see what we get. So we're going to separate this into 2 separate fractions. We're going to write it as 1 over sine theta, not plus, it'll be times cosine theta over sine theta. So when we have fractions multiplied like that, we just multiply the numerators together, multiply the denominators together. So you can see that those are the same thing. 1 times cosine is just cosine, and sine theta times sine theta is just sine squared theta. So those are indeed the same term. We've just broken the fraction apart a little bit. And while we're at it, let's rewrite that other fraction, the 5 times 1 plus theta squared. Usually it's helpful to try to separate any constant multiples from your variable part. So I might rewrite this as 5 times 1 over 1 plus theta squared. So just to kind of pull that fraction apart a little bit, put the constant term in front, and then we have all our variable stuff next to it. And we can worry about just integrating that variable part. All right. So now we can use some trig identities to rewrite 1 over sine theta and cosine over sine. So 1 over sine theta is cosecant theta, and cosine over sine is cotangent. So we get cotan theta. And then we have our plus 5 times 1 over 1 plus theta squared, d theta. And now we just go through and integrate term by term. So our terms are separated by plus or by addition or subtraction. So when I look at this, I see 2 terms again. I see the first term here, which is cosecant times cotan. And then I see the second term here, which is the 5 times 1 over 1 plus theta squared. So we just focus in on integrating each of those separate terms. And in this case, we'll add the results together. So we go for cosecant theta times cotan. This is something that shows up on our table now. So it's right here. So this is something we can do. And the antiderivative is negative cosecant x. Well, in this case, it'll be negative cosecant theta. So you just want to be consistent with your variable. Then we have a plus, and that 5 is a constant multiple, so it just stays in front. And then we really focus in on just integrating the variable part there, which is 1 over 1 plus theta squared. And we see that with a slightly different variable, but we see that right here. The antiderivative of 1 over 1 plus x squared is inverse tan x. So this would be arctan of theta. You could use arctan or inverse tan, however you want to do it. And then we put plus c at the very end. So we're just going through the term-by-term integration, rewriting things if need be, and then looking up anything that we're not sure of on our little list here of elementary forms. Let's try a few more. So it just comes with practice. So just like derivatives, the more you do of these, the quicker you'll be able to recall what these elementary forms are. So let's try 5e to the x plus x times square root x. And when we look at this, that x times square root x, we have some multiplication there. So if we were doing derivative, if we have multiplication, we have to use product rule. Or we could actually try and do the multiplication. And so the same thing kind of goes for integration. If we have a product, if we have multiplication, there's a rule, integration rule, that you'll learn in Calc 2 that tells how to integrate a product. But sometimes it's easier to just do the multiplication. And so for our course, 141, that's going to be our strategy, is if you can, do the multiplication and simplify as much as possible. So this x times square root x, what do we normally do with square root functions? Well, we rewrite it as raised to the power 1/2. And then when we have two power functions being multiplied together, we can add the exponents together. So this one it's kind of like a hidden 1, x to the power 1 times x to the power 1/2. We add the exponents together, and we get x to the 3/2. So sometimes you have to do a little bit of work before you get it into a form that's easy to do. We can easily calculate the antiderivative of. So if you have multiplication, we can't just integrate each piece of the multiplication there. We have to try and do the multiplication and get it into a power function or maybe something else. So you have to get it into one of our elementary forms. So with that, we've done just that. Now we're all set. 5e to the x is something we can do. It's a constant multiple of one of our elementary forms. X raised to the 3/2 power is just a power function now. It's not a product anymore. So that's something we can do. And then we're just adding those together. We can integrate over addition. That's no big deal. So when we look at this, we see first term, and we see a second term. And in that first term, we have 5 as a constant multiple. So the 5 just stays in front. And then we really focus in on the variable part there. And we want to know, well, what is the antiderivative of e to the x? Well, that's a nice one. Antiderivative of e to the x is just e to the x. So we get 5 times e to the x. Then we have a plus sign, so plus sign stays in our antiderivative, and then we do the power rule for x raised to the 3/2. So how does our power rule work? Well, our variable is x. We add 1 to the exponent, which bumps us up to 5/2. And then we take that new exponent and we flip it and put it in front. So 2/5. So our antiderivative here is 5e to the x plus 2/5 times x raised to the 5/2 power. And then we put 1 plus c there at the end. And we're done. All right, so sometimes you might have to do the multiplication in order to get it into a format that you can then integrate. Same thing if we see a fraction. Sometimes if you have division, it helps to just do the division if possible. So in part D here, we're going to be doing the integral of t squared plus 1 over t plus 7 times cosine t. And when we look at this, it's this first term here, this t squared over, or t squared plus 1 over t, that's going to present an issue. If we go to our table of elementary forms, I don't see that anywhere on our table there. T squared plus 1 over t. I don't see that on our list. So what we're going to do instead is we're going to do the division. So t squared plus 1 over t, we can break that apart. So we get t squared over t plus 1 over t, and then we can keep simplifying. So the t squared over t just becomes t, and then we have our plus 1 over t. So we can break up that fraction wherever we have a plus or a minus in the numerator. And so doing that division really kind of gets it into a format now that we can work with. So we get integral of t plus 1 over t plus 7 times cosine t, and we're doing that antiderivative now. So when we look at this, we're just going to go term by term, and each of the plus signs is really where the terms get split up. So when we look at this, this would be our first term, the 1 over t would be our second term, and then the 7 cosine t would be our third term. So there's 3 terms here, and we're just going to go down the line and integrate each of them. So first of all, what is the antiderivative of t? Well, that's just a power function. So we use power rule. Add 1 to the exponent, bumps us up to t squared. Take the new exponent, flip it, put it in front. So 1/2 t squared. That's our first term. Then we go to our second term. 1 over t is one of our basic forms. We can look it up if need be. So integral of 1 over t is just natural log absolute value t. And then that's our second term. We've done the antiderivative. Then our function had a plus sign in it, so we have a plus sign. And then we find the antiderivative of our third term. The 7 is just a constant multiple, so it just stays in front. And then we really just focus in on getting the antiderivative of our variable part, which is cosine t. So if we need to, we can go to our list, look up cosine, and see that the antiderivative is sine. So the antiderivative of cosine is sine. So we end up with 1/2 t squared plus the natural log of absolute value t plus 7 times sine of t, and then we put 1 plus c there at the end. Now, when we're doing this, the way we kind of read our work here, so there's a question, do we have to write f of x at the end or f of t or anything like that? You just want to be careful when using function notation. So we haven't really specified what the name of this function is, for instance. so we don't know what the name of that function is. So this is what I would write. I wouldn't write any, I wouldn't give, I mean, you could give it a name, but it's not necessary. And we don't know what the name of that other function is. Maybe it's g of t, so we're finding the antiderivative of g. So when we're doing this, this is the work I would show. The antiderivative of, so we're saying the integral of, we're saying this integral is equal to this integral by just some algebra that we did with our function, and then that integral is equal to this. So we're saying what our integral is equal to. So there's no need to kind of give this a name necessarily. So yeah, so on an exam, this is the amount of work that I would be looking for each of these. No changes. These would be perfectly good solutions on an exam. Yep, so this is about the amount of work kind of I'm expecting for these. Really it's if you have to do some sort of multiplication or division, I want to see that step. But in actually getting the antiderivative, there's really not much work here. You're just you have the integral, you get the answer. All right, so we're going to keep going with integration in learning outcome I2, but we're going to learn how to calculate something called the definite integral. And the way we're going to calculate this is with the fundamental theorem of calculus. So that sounds important. And it is. So that's what we're going to start with. The fundamental theorem of calculus. We're actually going to start with the second part of the fundamental theorem. And this is the one that we primarily use. So in most of Calc 1, Calc 2, and Calc 3, this is the theorem. This is the part of the theorem that gets used the majority of the time. So let's read through it. So it says, suppose that function f is a continuous function on an interval from a to b, and it has antiderivative capital F. Then we can calculate this gadget, which we call the definite integral of f from a to b, by this formula. So we'll read through the formula in a second, but this gadget here is our definite integral. And we'll see what this represents over the next couple weeks. We're going to be looking at some applications. We'll look at the precise definition of this. So we'll kind of get an idea of what this definite integral, what it really represents. Right now, we're just going to see how to calculate it. And the way we calculate it is by just looking at our upper limit here. So our upper limit is this b. We plug that into our antiderivative. We look at our lower limit, which is a, plug that into our antiderivative, and subtract. So the way we calculate this definite integral, it's the antiderivative evaluated at b minus the antiderivative evaluated at a. And these upper and lower limits, we also call these the limits of integration. So this is really related to what we were just doing with indefinite integrals. So how to calculate a definite integral, and again, we'll see really what this represents. There's different interpretations of it that we'll look at. Right now, we're just looking at how to calculate it. So the first step is to just get the antiderivative of the function. So that's step one. Find the antiderivative of the function inside the integral there. And we kind of do this in two steps. So we first get the antiderivative, and then to remind us that we're going to be evaluating, we use this vertical line that we write to the right of our antiderivative, and we put the lower limit on the bottom, the upper limit on the top. So really what this vertical line means is it means we evaluate. So this is just means plug in. And that's the second step. So the second step is then to just evaluate, and that's what the vertical line means. So we don't want to do too many steps all at once, so we kind of split this up. Step 1, find the antiderivative, then we write the vertical line, just reminding ourselves that we still need to evaluate. And then the second step is to do the evaluation. So the top number goes in first, then the bottom number goes in second, and we subtract. So that's what the evaluation looks like. Ends up being plug the top number in, plug the bottom number in, and we subtract. So that's how we're going to go about this. So a lot of the hard work is just finding the antiderivative, and that's what we just did. We saw how to find the antiderivative of a whole bunch of different functions. So that's the first step. The second step, once we have our antiderivative, is just to plug in. So this is how we're going to calculate this thing called the definite integral. And we'll, like I said, we'll see what this means. We'll see what some applications, some interpretations of what this definite integral actually is. But right now we just want to work on being able to calculate it. Now one thing that's going to be important is, especially going into Calc 2, is that our function f needs to be continuous on the interval. So if it has a discontinuity on that interval, you might run into trouble. So we mention it now. We're going to revisit this in Calc 2. What happens if we have a discontinuity? But this is something we want to just keep in the back of our minds, check as we're trying to integrate a function. Is our function continuous on that closed interval from a to b? All right, so let's kind of relate this back to what we were just doing. What's the difference between indefinite and definite integrals? So when we do an indefinite integral, the notation is very similar. We use that integral sign, the dx. The only difference is we don't have the little numbers on our integral sign. And so the end result for indefinite integrals is the result is a function. So when we do an indefinite integral, you should have, in most cases, you should have variables there in your answer. And we use plus c. So our final answer for doing an indefinite integral normally has a constant plus c at the end. Now for a definite integral, as we're going to see, notation is very similar, but we have these little numbers, these little limits of integration that go on the ends of our integral sign. And the end result for a definite integral is we don't actually end up with a function, we end up with a number. So the result here, once we go through the process of calculating a definite integral, the result is going to be a number. And we'll see what that number represents over the next couple weeks. But for right now, we're just going to be calculating it, trying to get that number. And when we do a definite integral, we do not use plus c. So that's primarily the difference. An indefinite integral is a function. Your answer should have variables in it in most cases. A definite integral is going to be a number, so you shouldn't have any variables. And you're not going to be using plus c for a definite integral. So the question is, why do we not use plus c for a definite integral? And I mean, you can. If you want to use plus c in your work, you can. It just complicates things for doing a definite integral. And we normally choose plus c to be 0 in this case. So that fundamental theorem of calculus, it works with any antiderivative. So to make things easier, we normally pick c to be 0 for calculation purposes. So why doesn't it really matter? Well, if we were doing the antiderivative of, give myself a little more room here. If we were doing this definite integral from a to b of little f of x, and let's say we use the plus c, and then we're going to evaluate from x equals a to x equals b. Let's plug in. So the top number would go in first, would give us f of b plus c. Then we plug in the lower number, so that would give us f of a plus c. And when we do the subtraction, we have a c and a minus c. They end up just canceling anyways. So we would end up with the result of f of b minus f of a. So in order to make things easier, we just don't use plus c, or we think of it as setting plus c equal to 0. It's going to get canceled out anyways. So in order to kind of help us along, make sure we don't make any little mistakes here and there, it's easier for definite integrals to not use the plus c. So if we think of it in terms of graphically, the plus c just gets canceled out. And we can see that. What are we doing? Let's suppose we had some function, antiderivative f of x, and we just wanted to look at the change in that function over the interval from 0 to 1. So the change in that function from 0 to 1, graphically, would be the difference in the height of these 2 points. So f of 1 minus f of 0 is just this vertical distance here, just the difference in the height of those 2 points. Now, if we just move that function up or down, that change in height is still going to be exactly the same. So let's suppose that we had f of x plus some constant and wanted to look at the change in that function from 0 to 1. Well, our starting point has been bumped up c units. Our ending point has been bumped up c units. And so sort of the net change here is just the difference in the height of those 2 points. And it's the exact same kind of length. So shifting our antiderivative up c units doesn't do anything to the net change in our antiderivative. And you can kind of see that graphically there. All right, so let's get a little practice. So we've talked a little bit about, what this definite integral is. The result should be a number. Let's go through now, look at a few examples of just calculating these out. So the first one here, let's do the definite integral of the function x squared over the interval from 1 to 2. First thing we just want to mention or note is that the function we're integrating here, x squared, is continuous, and it's continuous on that closed interval from 1 to 2. All right, so just means we can go through the process as is. All right, so step one, we find the antiderivative of our function. So x squared, that's just a power function. We use the power rule. So what's the antiderivative? Well, our variable is x. We add 1 to the exponent, which bumps us up to 3. Then we take that new exponent, flip it, put it in front. So the antiderivative we're going to use is 1/3 x cubed. Normally we would write plus c, but because we're doing a definite integral, we don't need to use that, or we can set plus c equal to 0. Then we write our vertical line, which means we're going to evaluate in our next step, and we're going to evaluate from x equals 1 to x equals 2. So step one here is to find the antiderivative. Step two is to then evaluate. So the top number goes in first. So we get 1/3 times 2 cubed. Then we subtract, and then we plug in the lower number. So the lower number is 1, and when we plug that in, we get 1/3 times 1 cubed. And that's it. So there's our definite integral. We can clean that up a little bit. So what we did there is the evaluation. So that's the second step of doing this. Just plug in the numbers into your antiderivative. Now it's helpful to try to simplify this down a little bit. So the 2 cubed times 1/3 gives us 8/3. And then the 1 cubed is just 1. So we get 8/3 minus 1/3. And then if we do the arithmetic there, we end up with 7/3. And that's our answer. So for a definite integral, whatever you get at the end, it should be a number. No plus c that you put on. We're not going to write a plus c here. The answer is just a number. No x's anymore. Doing the antiderivative and then plugging in gets rid of the x's. So the end result is just a number. Let's try another one, just to go through the practice of finding the antiderivative and then plugging in. So let's look at the next one, which is the integral of the function e raised to the power t from -1 to 1. We just first note that we're dealing with an exponential, and it is continuous on that closed interval. So we can evaluate this definite integral by this process of finding the antiderivative and then plugging in. So let's find the antiderivative. E raised to the power t is one of our nice ones. It's its own antiderivative. So just e raised to the power t. And then we evaluate from -1 to +1. Again, this is just step one here of finding the antiderivative. Once we have the antiderivative, step two then is to actually plug in. So when you do this, it's very easy to there's going to be subtraction, and it's easy to kind of lose track of things. So it helps to just kind of set up the framework for what you're going to be doing. So it's going to be the top number plugged in, then you have the subtraction, and then it's going to be the bottom number plugged in. You kind of get that all set up, and then you go about plugging things in. So what do we get when we plug the top number in? Well, you get e raised to the power 1. What do you get when you plug the bottom number in? You get e raised to the -1, and you're subtracting. And then if you clean that up, e to the 1 we don't normally write, so it's just e minus e to the -1. And again, there's no variables, it's just a number, and there's no plus c at the end as well. So the second step there for our work is just evaluating. Top number, plug the top number in, subtract, and then you plug the bottom number in. All right. Let's try one more, just for the practice. We're going to do the integral of 1 over x squared over the interval from -1 to 3. And first thing we want to check is this continuous. And it's not. So we can't. We can't go any further. So we cannot use fundamental theorem of calculus part 2. So there's no way for us at the moment to figure out if this integral, what this integral is. And the reason is because the function 1 over x squared is not continuous. And it's not continuous in a very difficult method to handle. It has an infinite discontinuity. So it has a vertical asymptote at x equals 0. So we're going to see how to handle things like this in Calc 2. This is what we call an improper integral. But for right now, if we have a discontinuity like this, where our function has a vertical asymptote, and that vertical asymptote happens inside the interval, then we can't do it. So, for instance, if we wanted to do the integral from 2 to 3 of 1 over x squared dx, this one we could do. We could do that. And the difference is that 0 is not inside the interval from 2 to 3. So why were we running into trouble in that first one? Well, 0 is right there in the middle. It's inside that interval from -1 to 3. It causes an issue. We can't use the fundamental theorem of calculus. But if we are looking at that same function, 1 over x squared, on just the interval from 2 to 3, well, on that interval, we don't run into that issue of having an infinite discontinuity because 0 is not between 2 and 3. So that one we could do. So it's just kind of important to keep this in mind when you're doing a definite integral. I won't be giving any trick questions like this one, but it's just important to recognize that. And you're going to see this again in Calc 2. There's a whole nice big topic on it called improper integrals. And you see how to handle things like this. So it's important just to note that here, though. All right, so that's basically it. That's basically how we're going to be calculating these definite integrals. The difficult thing is just getting the antiderivative. But once you have the antiderivative, it just comes down to evaluating. And so we have some properties for definite integrals. And we're going to look at these 3 properties here, which really it just inherits from our indefinite integrals. So these are all ones we've already looked at. So these 3 properties are just properties that are inherited from the indefinite integral. So what this means is that when we go through finding the antiderivative, our strategy, our term-by-term integration strategy that we did for indefinite integrals, we can do the same idea for definite integrals, and it applies. So for instance, these first 2, just say if we have a plus sign or a minus sign, we can just split up our integration wherever we see a plus or a minus. So wherever we have addition or subtraction, we can split up our integration. And then the last one is our constant multiple rule. We saw that with indefinite integrals. It still applies for definite integrals. So if we have a constant multiple, we can bring that constant multiple out and put it in front of the integration. So we can just focus in on integrating the x term first and get the constant term, the constant multiple term out in front. So these are really just properties that the definite integral inherits from the indefinite integral. But really for our purposes, it means we can go about integrating things business as usual. So for instance, if we had the definite integral of 3 times cosine t plus 2 from 0 to pi over 2, we can really just kind of think of finding the antiderivative along our normal procedure of just going term by term. And that's what we're going to do. So if we wanted to do the find this definite integral, first step is to just get the antiderivative. So when we look at this, sort of a first term here, there's two terms. Our first term is this 3 times cosine t. Then we have a plus sign. And then after our plus sign, we have our second term, which is 2. And we just go term by term. So in that first term, the 3 is a constant multiple, so it just stays in front. And then we really just focus in on getting the antiderivative of that variable part. And the antiderivative of cosine is sine. So the antiderivative of that first term is 3 times sine t. Then we have a plus sign. And then for the second term, we're integrating just a constant. So the antiderivative of 2 is just 2 times t. So integration kind of puts variables back in. Derivatives kind of takes variables away. So when we integrate a constant term, we're going to put a variable onto it. If we are differentiating 2, derivative of 2 would just go down to 0. So integration sort of builds your function back up in some way. So the integral antiderivative of 2 is 2 times t. That's step 1. Then we're going to evaluate from 0 to pi over 2. And that's our second step. So we put that vertical line to indicate that we're going to do the evaluation. And this is step 2, actually doing it. So the top number goes in first. We get 3 times sine of pi over 2 plus 2 times pi over 2. So that's what happens when we plug the top number in. Then we subtract, and then we plug in the bottom number, the 0. So we get 3 times sine of 0 plus 2 times 0. And that's our definite integral. That's it, that whole thing. If we can, though, it's helpful to simplify. So sine of pi over 2 is just 1. Sine of 0 is just 0. So this whole thing ends up being 3 plus pi. And that's it. So good to try to simplify as much as possible, just to kind of get your number in simplest format there. And notice that we don't have any variables, so the answer here is just a number. Let's try another one. Let's do the definite integral of 2x cubed minus 6x plus 3 divided by x squared plus 1. And we're going to do the integral from 0 to 2. Now, in the back of our minds, we see fraction. You might start thinking, let's make sure we're not dividing by 0 anywhere. But x squared is always positive, plus 1 is always positive, so we can never divide by 0 there. X squared plus 1 is always going to be greater than 0, so we can't divide by 0. So there's no issue here with having a discontinuity. All right, so first step is to get the antiderivative. So when we look at this, what are we seeing? We have a first term, we have a second term, and we have a third term. So we're just going right down, we're going to go right down the line and just do the antiderivative of each of those terms. And that's our first step, is just finding the antiderivative. So let's start with that first term. The 2 is a constant multiple, so it just stays in front. And then we get the antiderivative of our variable part, which is x cubed. So that's just basic power rule. Variable is x, add 1 to the exponent, which is 4. Take that new exponent, flip it, put it in front. So we end up with 2 times 1/4 x to the power 4. That's our antiderivative of our first term. Now we're done with that. We go to our second term. So we have subtraction. Then that 6 is a constant multiple, so it just stays in front. And then we get the antiderivative of our variable part. So antiderivative of x, another power rule. So variable is x, add 1 to the exponent, bumps us up to 2. So we have x squared. Take that new exponent, flip it, put it in front. So 1/2 x squared. So that's our antiderivative of our second term. Then we go to our third term, and that plus 3, that 3 in the numerator, is really a constant multiple. So we can have the 3 as our constant multiple. And, you know, if you want to think of it, we could think of the 3 over x squared plus 1 as really 3 times x squared plus 1. And so that 3 is a constant multiple, and then we really just focus our attention on finding the antiderivative of 1 over x squared plus 1, and that's one of our elementary forms. That's arctan. So there's our antiderivative. We're done with it. We're done getting the antiderivative. We went term by term and found it. We still need to do the evaluation, so we write our vertical line indicating that we're going to evaluate. Before we do the evaluation, it's helpful to try to simplify your antiderivative as much as possible. So, you know, some of this arithmetic you may have already done, but let's write it out with the simplified, in a simplified format here, just to make our evaluation a little bit easier. So like that 2 times 1/4, that'd be 1/2. So it'd be 1/2 x to the 4th. And then we have minus, and then 6 times 1/2 would just be 3. So we have minus 3x squared plus 3 arctan of x. So it's helpful to try to simplify, if possible, try to simplify your antiderivative down as much as you can before you evaluate. So that's all we did there. Not absolutely necessary, but it tends to be helpful. Try to simplify as much as possible. Now we're in a position where we can just plug in. So that's the next step. Let's evaluate this thing. So the top number goes in first. And when we do this, you know, it might be helpful to try to kind of just write out the format here. It's going to be the top number minus the bottom number plugged in. So what do we get when we plug that top number in? Well, it's going to be 1/2 times 2 to the 4th minus 3 times 2 squared plus 3 arctan of 2. So we plug the top number in first, then we subtract, and then the 0 goes in. So we get 1/2 0 to the power 4 minus 3 times 0 squared plus 3 arctan of 0. And then we just clean things up. So we end up with 8 minus 12 plus 3 times arctan of 2. Arctan of 2, No, it's okay to leave it like that. Arctan of 0 is just 0. So this whole thing, anything times 0 is 0, anything times 0 is 0. So this whole second piece here just becomes 0. So simplifying, we just end up with -4 plus 3 times arctan of 2. And again, that's just a number. So that's the value of our definite integral. So let's try one more example of doing these definite integrals. So we're going to do the definite integral of the function 3x minus 2x cubed over 4x to the power 4 over the interval from 1 to 3. And the thing we see here is that we have a fraction. So our strategy for dealing with these is to try to do the division. So our strategy is to do the division first. So before we start even doing antiderivatives, we're going to rewrite our function, and we can split this fraction up into two separate fractions. So we can write it as 3x over 4x to the power 4, then minus 2x cubed over 4x to the power 4. So we've just split it up into two separate fractions. And then from here, we simplify. So try to simplify as much as possible. And we can cancel some of the x's. So in that first fraction, we simplify and we end up with 3 over 4x cubed. So one of the x's cancels. And then in the second fraction, we end up with 1 over 2x. So the 3 of the x's cancel, and then some of the 2's cancel. And then we don't want to forget our dx there at the end. So we want to integrate this. And whenever we're dealing with constant terms and x's, we want to try to separate the constant multiples from the x terms. And that's what we're going to do. We're going to separate our constants from the x's. So when we look at this, we still haven't done any antiderivatives. This is all just working with our function. So for that first one, I'll pull off the 3 over 4 and write that as 3 over 4 times 1 over x cubed. And then I'll do the same thing for the second fraction. I'll pull off the 1 over 2 and write that as 1 over 2 times 1 over x. Just to get it into the format of a constant multiple times an x term. Still not ready to integrate. So we have that 1 over x cubed. And so what we normally do is we use negative exponents. And we're going to use negative exponents for everything, but whenever we have a 1 over x, we'll leave the 1 over x as is, because that's its own special antiderivative. Excuse me. All right, so for that 1 over x cubed, we'll write that as x to the minus 3 instead. So it's 3/4 times x to the minus 3. Then we have minus 1/2, and I'm going to leave that 1 over x as is. We handle that differently. So x to the minus 3 we can use power rule for. 1 over x, that's something different. All right, so from here, now we're ready to integrate this. So each of those terms is a basic antiderivative. power rule or just one of our elementary forms. So now we're ready to get the antiderivative. So we don't write the integral sign anymore. Once we start finding the antiderivative, the integral sign drops out. So the antiderivative of 3 over 4 times x cubed, this is our first term here. And it's a constant multiple times an x variable, x term there. So our constant multiple stays in front, and then we just get the antiderivative using power rule. So we add 1 to the exponent, bumps us up to -2. Take that new exponent, flip it, put it in front. So -1/2. So that's the antiderivative of our first term. Then we go to our second term. The 1/2 is a constant multiple, so it just stays in front. So we're going to end up with -1/2. And then the antiderivative of 1 over x is just natural log absolute value x. And I'm going to go over a few minutes today just because we have this example to finish and then just a little bit extra. So I'm going to go over by a couple minutes. So I apologize in advance, but just so that we don't kind of have to split this lecture up over a couple days, I'm going to finish it off in the next few minutes. So we're going to go a little bit extra today. So there's our antiderivative. And we're not writing the dx anymore. We're not writing the integral sign anymore. Instead, we have our antiderivative, and we're going to evaluate this from x equals 1 to x equals 3. So that's kind of the first step for actually doing this definite integral is that's the antiderivative. Now, before we plug in, we want to simplify. And plugging in, negative exponents are okay, but actually evaluating, sometimes it's a little bit easier if instead of using a negative exponent, we convert back to a fraction. So that's what we're going to do. So we'll write this as -3 over 8. Just consolidate those fractions in front. And then instead of 1 over x, or x to the -2, I'm going to write that as 1 over x squared. Sometimes that makes evaluating just a little bit easier. And then we have -1/2 natural log absolute value x. And then we evaluate. So we've simplified it down. That's about as far as we can go simplifying. And so now we plug in. So the top number goes in first. Bottom number goes in second, and we subtract. So when we plug the 3 in, we end up with -1 over 24 minus 1/2 natural log 3. Absolute value 3, but absolute value 3 is just 3. Then we plug the 1 in, and we end up with -3 over 8 minus 1/2 times natural log 1. Natural log 1 is just 0. And we go through and simplify if possible. So if we kind of combine any fractions, get a common denominator, what we end up with here is 8 over 24 8 over 24 minus 1/2 natural log 3. So that's really our main second step there, is to just do the evaluation. And sometimes to help with the evaluation, you want to simplify your antiderivative down as much as possible. And if you have negative exponents, sometimes it's a little bit easier if you convert those back to fractions as well. All right, so we end up with a number as our answer, though. So that's important. All right. So we're just going to look at a couple other properties of definite integrals, and these ones involve the actual limits of integration. We're going to touch on these again a little bit. But for right now, if we're integrating from a to b, we can reverse the order of our integration, and that introduces a minus sign in front. So if we switch the limits of integration, what we do is we put a minus sign or negative in front of our integral. So we can switch the limits of integration, but it does change the value of our definite integral. It makes it negative. So we put a negative in front. Another nice little property is if we try integrating a function over and the limits of integration are the same, well, the definite integral ends up being 0. So if the upper limit is equal to the lower limit, the integral is 0. That's just another handy one that sometimes is useful. And then the last one there, and we'll see how to do this, how to apply it. One way to apply this in the next example is sort of a property that allows us to consolidate or split up integrals. So what does it say? It says if we have the integral from a to m plus the integral from m to b, and the key thing here is that those numbers are the same, well, then we can just combine those and say, look at the integral from a to b. So you can think of this as sort of like getting rid of the middleman. So if we have an interval, think of our x-axis here. And we're interested in going from x equals a to x equals b. What this property says is if we went from x equals a to x equals m and looked at just that integral, then we went from m to b and looked at just that integral, well, it's the same thing as just saying, let's just go all the way from a directly to b. We don't need to stop over at x equals m. So we could do the integral from a to m, do the integral from m to b, or we could just go all the way from a to b and we should get the exact same result. So that's what this third property says. So let's see how we would use it. One possible type scenario. Let's say we want to calculate the integral of some function from 0 to 5. And we know the integral from 0 to 6 is equal to 8. And the integral from 5 to 6 is equal to 7. We want to figure out that unknown integral from 0 to 5. So really what we want to do is we're thinking of it in terms of, we want to think of these definite integrals in terms of really intervals. So we have our x-axis, and we're interested in the integral from 0 to 5. So this is what we don't know. We're interested in this, the integral over that interval. So we're interested in knowing what is the integral from 0 to 5. Well, we know the integral from 0 to 6 so we know that. If we're going from 0 to 6, we know what the integral over that interval is. And we know what the integral is from 5 to 6. So using this property, we know the integral from 0 to 5 plus the integral from 5 to 6. And since these limits of integration, 5 and 5, are the same, we're covering the exact same portion of our x-axis, it has to be equal to the integral from 0 to 6 if we just go all the way. So we just kind of fill in what we know and leave what we don't know. So we don't know the interval from 0 to 5, so we're just going to leave that as the integral from 0 to 5. We don't know that one. But we do know the integral from 5 to 6 is equal to 7, and we know the integral from 0 to 6 is equal to 8. And so this is just some unknown value. And so the way you solve an equation for an unknown value is just get all the other terms over to the other side. So we would subtract 7 from both sides. And that gives us the integral from 0 to 5 of f of x dx is equal to 1. We're just solving for that unknown value. So subtract 7 from both sides, and that moves it over. And that gets it by itself. All right, so I apologize for going over a bit there, 10 minutes or so. I just wanted to finish that up so we can kind of start on a new topic on Thursday. I'll shorten up Thursday's lecture to kind of make up for going over today. So I don't want you to, have more time than needed here. But I thought it'd be good while we're kind of on the topic of these definite integrals. Let's just kind of keep going. All right, so we're going to stop there for today. Reminder, we do have homework due tonight. So on Learning Outcome 05, homework due Thursday is on 06, so the constrained optimization problems. And then we're going to have some integration problems, problem sets due next Tuesday. So I1 and I2. And then on Thursday, for Thursday's lecture, we're going to start substitution rule. So that's kind of one of our big integration rules that you're going to use for the rest of this course. You're going to use throughout Calc 2, and then if you go into Calc 3, you're going to see it there as well. So substitution rule, this is going to be a big one. So these few topics of integration are going to really kind of lead over into Calc 2 for next semester. So anyway, we'll stop there for today. Have a good rest of your day and rest of your Wednesday, and then we'll see you all on Thursday. Bye-bye.